Function notation. Okay, so we're going to be looking at writing functions in function notation and looking at the graphs and relating it to whatever the context of the problem is. So the first question we have here is about braking distance. So we're going to start on how long will it take for the car to stop. So if you have ever been in a car when the driver slams on the brakes, you know that the car does not come to a stop immediately. Braking distance refers to the distance a vehicle will travel from the point when its brakes are fully applied to when it comes to a complete stop. Okay? So what factors do you think affect the car's braking distance? Speed. Yes, that's one. What else? The weather. If it's rainy, if the road's wet, it can affect it. What else? The weight of the car. A Honda Civic stops faster than a Ford F-250. What else? Yeah, speed.
How hard you're pushing on the brakes. It's like if your brake pads.
Yeah, your brake pads, if they're new or if they're really worn. Okay, all of those things affect it. Okay, we're specifically going to look at how speed affects braking distance today. Okay, so we are given here, the graph shows the relationship between a car's speed and its braking distance. Some values are also given in a table below. So first, is speed or braking distance Rx? Speed. Okay. So that means that's our input. Okay. Is speed or braking distance Ry? It's Ry. And that is our output. Okay. So we're going to look first at what is the braking distance of a car driving 60 miles per hour? 171 what? 171 feet. Where'd you get that from? The table. You could have also got that from looking at the graph. So when 60 miles per hour, you can go and look at where that is on the graph. So it'd be like right here, which is about 171. Okay. So now, the next question is, what is the braking distance of a car driving 40 miles per hour? How do we know? So what is the braking distance of a car going 40 miles per hour? It's not on the table, so look at the graph. What's the braking distance when it's going 40 miles per hour? 75, yep. 75 what? Feet. How do you know that? The graph, right? The graph shows us that. When the speed is 40, the braking distance is 75. All right. Now, it says the ordered pair 73, 254 is on this graph. What does it tell you? So let's look at first where that points at. So 73 and then 254, somewhere in that region. What does that tell you? What does the 73 represent? Speed. So at 73 miles per hour, what is the braking distance? 254 feet. The braking distance is 254 feet. Okay, now, a car took 200 feet to come to a complete stop. Estimate the speed at which the car was traveling. So it took the car 200 feet to come to a complete stop. So if I look at that on the graph, how fast were they going? 65. Yeah.
Like 6, 7?
There you go, yeah. Everyone has made that joke. On first period, I actually wrote it. It was 65 miles per hour. Okay. So we're going to stop there, and we're going to go on and look at function notation before we come back and do those questions. So I want us to go ahead and jump to the back page. when we're looking at function notation, we are looking at this, okay? When we're talking about function notation, this is usually what we are talking about. And so, equations that represents functions can be rewritten in function notation. So, normally if we write the equation of a line, we would write y equals mx plus b. A line is a function, so we can rewrite that using function notation by doing f of x is equal to mx plus b. It lets us take the y and replace it with function of x. That's just a more specific name that lets us know, hey, that is a function. Because is every equation a function? No. To be a function, each input can only have one output. So it tells us it's a specific type of equation that has certain properties by us using that notation. So we read that notation as f of x. That's how we read it. And when we look at this, x is the input, just like normal, and f of x is the output. F of x takes the place of our y value, okay? F of x and y are the same thing. They're both the output. It's just f of x tells us specifically, hey, this is a function in terms of x. Not just it's an equation. It says it is a function. It makes it more specific to the question we're talking about. So now we're going to look at evaluating functions. So evaluating a function means finding the input or finding the output that corresponds with the given input. So I have rewrote that question on the board over here, and it says evaluate y equals 4x minus 1 at x equals negative 7. This is a question we have done before, and we'll do again. What would you do in this question? I'm just going to plug in negative 7 for x. So I would get y is equal to negative, or not negative 4, 4 times negative 7 minus 1. This right here is the exact same question that we have in our notes. It's just written differently. It's written in function notation here. So instead of saying evaluate y equals 4x minus 1 at x equals negative 7, this just says if the function f of x is equal to 4x minus 1, find f of negative 7. Okay? Right here, that tells us what our x needs to be. What is our x? Negative 7. It's just a way of us writing it in a little bit shorter of a way. Okay? So we're going to evaluate that function where? At negative 7. So we're going to do f of negative 7 is equal to, when I plug something in, what do I always need to put around it? So we're going to do 4 times negative 7 minus 1. All we did was replace x with negative 7. Then we just evaluate it. What is 4 times negative 7? So we have negative 28 minus 1. What is negative 28 minus 1? Negative 29. So when we do that, the negative 7 is our input. It's what we're plugging in. And the negative 29 is our output. It's what we're getting out. So we are just plugging in numbers. That's all we're doing with this. It's just we're writing it in function notation. Okay, same thing. So we're going to go ahead and we're going to do some examples of this. We're going to skip around through the questions because there's a few that I want to make sure we do together before I let you do some on your own. Okay, so we're going to look at number 2. So number 2, what is the x I need to plug in? Negative 3. So x is our negative 3 right there. So I'm going to take and go g of negative 3 equals 3. What do I need to put there? But to plug it in, what do I need to use? Parentheses. Minus 8. Now, what is 3 times negative 3? So we get negative 9 minus 8. What is negative 9 minus 8? Negative 17. Okay. I want to specify something that we make sure we remember. When we write this right here, even though we're using parentheses, am I multiplying? No. This is just the notation we use. Okay. G of negative 3 just means, that's just what it is. It's the function G at negative 3. That's just a way to write the name of it. Okay. I just want to make sure we know that. Now I want us to look at question 3. So question 3 is a little differently. Does question 3 plug something in for x? No, it takes the whole function and sets it equal to what? 9. So this is changing the output. So all I'm going to do is that same thing. I'm going to take the whole function and set it equal to 9. So instead of h of x, I will use 9 equals 2/3 x minus 1. And then I'm going to solve it to find the input. So how would I solve that? Plus 1. What is 9 plus 1? Equals 2/3 x. How do I get rid of a fraction? What's the reciprocal? So what is 10 times 3? Or 30. What is 30 divided by 2? So 15 is equal to x. We're able to solve for what our input is for an output. Then we're going to look at question 4.
I thought you multiplied from both of them, not just the top one.
So it's technically over 1.
Okay.
So it would be 3 times 10, which is 30 over 2. Yep. All right. Now, for number 4, okay, what do I need to plug in for number 4? Negative 4. X is equal to negative 4. That's what we have. So I'm going to have f of negative 4 is equal, I'm going to use, what do I need to do to plug in? Parentheses, negative 4 squared minus parentheses, negative 4. What is negative 4 squared?
16.
Positive 16, because a negative and a negative make a. Then we have a negative and a negative, which gives us positive 4. So it is 20. So our input is negative 4 and our output is 20.
We have to put input and output.
I just want us to be able to recognize it. All right. Then we're going to look at question 6 together as well. For 6, what are we plugging in for x? What is x for 6? A plus 2. So we're going to plug in a plus 2 everywhere there's an x. So we'll have 4 times a plus 2 plus 11. What do you think I'm going to do from here? Distribute. Okay. What do I need to distribute?
4 and
So 4 times a is?
4a.
4 times 2 is? Then we have, is there anything happening with plus 11?
You added to it.
So I bring it down. So we get f of a plus 2 is equal to,
4a minus 19.
because we combine our like terms. What are our like terms? 8 and 11. All right.
That's it?
That is how we do function notation, yeah.
What is your input?
So in this case, our input
Is it 4?
is a plus 2. That is our input.
And your output is
Then is our output is everything that's over here. That whole thing is our output. Okay, output can be, like your input can be as simple as a 1, or it can be as complicated as a whole other function. We can input anything into that, okay? So I want y'all to do 1 and 5 for me real quick. So do number 1 and number 5. Do both of those for me real quick. For number 1, what is f of 5?
12.
Because x is 5, so that's what I got to plug in. So I get 5 plus 7, which is 12. All right. All right, what do I have to plug in for number 5? -8. So we get -1/2 times -8 plus 9. So a negative and a negative make a, and what's half of 8?
4.
So +4 plus 9 is
13.
13. G of -8 is 13. All right, so that is how we do function notation, okay? I want us to go back and do function notation for all of those questions that we did on that first page. So we're going to start with that first A. Okay, it says, what is the braking distance of a car driving 60 miles per hour? We said it was 171 feet. So if I wanted to put that in function notation, f of, what is my input? 60. And then what is our output? 171. So we evaluated these without even realizing that's what we were doing. Okay, so for the next question, what would the function notation be for that one? So f of 40 equals 75. All right. For the ordered pair, how would I put that ordered pair in function notation? F of 73 equals 254. Yep. F of 65 equals 200. All right. Now, we're going to do those stop questions. So it says find f of 50 or f of 80. Okay, so if they're going 80 miles per hour, I'm going to go ahead and tell you 80 is technically the line that's out here. It just doesn't do a good job of showing that. That's technically where your 80 is at. It's just 300, yeah. We can just do 300.
It's on the data chart.
Oh, it is? Oh, fun. That helps. 305. All right. So, it wants us to then put it in context of the problem. So, what was our input? 80. So, at 80, what? At 80 miles per hour, the braking distance is 305 what? Not just feet. Okay, then It says use function notation to express that a car traveling 45 miles per hour will require a braking distance of 96 feet. How would I write that?
45 equals 96. Do I have to write it too?
We just have to write it like that because it already tells us in context. We just want us to put it in function notation. All right. So we're going to look at evaluating, giving a graph. So we're going to skip over questions 7 through 12. And we're going to go ahead and look at evaluating given a graph. We've already done this. We did this on the braking distance problem. Okay? It's the same idea. So I want us to look at this first example we have. Okay? So the first thing it says, a graph of y equals f of x is shown. That just tells us that the function on this graph is f of x. That is the graph of f of x. Okay? We have our x-axis. We have our y-axis. So from here, we're going to evaluate the function. So A says find f of negative 2. That means our x is what? Negative 2. So when x is negative 2, what is y? 0. So when x is negative 2, where is it on that graph at? 2. That's where that point is located. So at f of negative 2, it is 2. We are finding where those points are on the graph. Okay? And when we talk about the graph, we're not talking about the x and y coordinate. We are talking about the actual thing drawn on the coordinate. Okay? So for part B, it says find f of 1. So we're looking when x is 1. So when x is 1, what is y? 3. Okay, then C asks it backwards. Instead of saying when x is something, find y, it's saying when find x when y is 6. Okay, that's what that's saying. So if f of a equals 6, find the values of a. So we're looking when y is 6. So y is 6 up here. So that is the point I'm looking at. What is x when y is 6? 5. So a equals 5. All right, and we're going to do question 13 together. So for question 13, we're going to start with f of negative 3. So that's telling us to find y when x is negative 3. So when x is negative 3, what is y? 2. Okay, for B, it's saying if f is 0, f of 0, find y. So at 0, what is our y value? So then we have f of 1. So that's saying when x is 1, find y is 2. Okay, then it gives us one of the weirder questions. So find if f of a equals negative 3, find a. So negative 3 is our x value or our y value? Y value. Okay, it is down here. It is negative 3. How many points are on this graph at negative 3? 2. That's outputs. That's okay. We can have repeat outputs. But what are the inputs that give us negative 3? There's 2 of them. Negative 4 and 2. So the reason that is okay is because outputs in a function can duplicate. So remember our birthday example? Who all in here has a birthday in October? Anybody have a birthday in October? A birthday in November. Okay? So how many birthdays does Jaden have? 1. Okay? How many birthdays does Trinity have? 1. Each input has only 1 birthday. But can 2 people have November birthdays? Yeah, that's okay. Outputs duplicating is fine. It's still a function. It's as long as your input is unique. And in this case, our inputs would be a -4 and a 2. All right, so I want you all to do the same thing for 14. I want you to do all of 14 for me real quick. Yes. All right, what is f of -4? 2. Okay? Because our point is here, and our y value there is 2. Now, what is f of what is f of 2? -2. Okay? What is f of 0? 0. Now, the last question was f of a equals 1. How many places is our y value 1? 3. What are those 3 places? What x values? -1, -5, and 6. So that should be our 3 answers. All right. So we have about 20-ish minutes left. Okay. So we're going to finish up 3.2 and talk about context again. Okay. We already did this. Okay. Basically, we did all of the parts of today's lesson in the braking distance problem. Now we're just talking about it specifically in each piece, okay? So, interpreting in context. In order to interpret in context, you must identify what the input and output represent within the context of the problem. One of the most important things in the context is that you use proper units. Okay? If in the braking distance problem, we wouldn't have said feet, we said miles. And suddenly the braking distance is 300 miles. Does that make any sense? No. Context matters. The units we use matter. Okay? So, or what if instead of miles per hour, we did miles per second? That would be wild, wouldn't it? What if you have to make sure your units are correct, because that changes what the question means, what your answer means. It can take it from something that makes sense to take it to something that makes no sense, that at 80 miles per hour, it takes 300 miles to stop. That would be a problem. No one would ever need to drive if that was the case. Okay, so for question 15, okay, we're going to start just by finding the input and output before we even worry about solving the problem. So let's read it. Anthropologists use the length of certain bones of the human skeleton to estimate the height of a living person. Okay, one of the bones they can use is the femur. So to estimate the height in centimeters of a female with a femur length of x, they give us a function. So before I do anything else, what is my input? What is my x? Not the question. I don't want to worry about the equation. I just want to worry about the context. It's the femur length. Because it says femur length of x, right? That is telling us explicitly the femur length is our input. Okay? So what does that mean our output or our y is? The height. So in this question, okay, it doesn't use y, it uses h of x. It's a function of height, so h of x, okay? And what was our units? Centimeters. All right, so now I'm going to actually look at the question. It says the function h of x is 61.41 plus 2.32x can be used. And then it says find, that is supposed to say right there, h of 46. And explain what it means. So for using this part, what does h of 46 tell us we need to do? Replace the x with 46. So we're going to do 61.41 plus 2.32 times 46. So someone use their calculator and tell me what that's going to equal. But how big is the question? $168 point what? And our units is what? So that is approximately 5.5, by the way. So how would I answer this in context? At what does 46 represent? Okay. Let's do a female with a 46 centimeter femur is about how tall? We just answered it. And that would be how we would answer it in context. Okay, this part is not necessary for us to answer for the question, but it is necessary for us to understand. We have to be able to read a question and go, okay, this is our input, this is our output, and recognize units and anything else that's important in that. Okay, so we're also going to do 16. Okay, so for question 16, it says let N of T represent the number and people in line at a barbecue food truck T hours after the food truck opens. So would T be our input or our output? Input. It's literally in the function. So that means it's our input. Okay. So it's T hours, and that is our input. Okay. Then N of T represents what? So T is hours, and then N of T is, it's our output, and that's our, what is it measuring? Number of people. It's the number of people in line at that many hours after they open. Okay, and that's our output. So we're going to answer all of these questions in context. We're just going to say what they mean. Okay, so for A, what does N of 1 equal 11 mean?
After 1 hour, 11 people were at the food truck.
After 1 hour, 11 people were in line. Okay, then it has N of 0 equals N of 3. What does that mean?
After 0 hours, 3 people were in line.
No, because it has N of 0 and N of 3. So what is N of 0? So what does 0 mean there? 0 hours after they open. So that would be as soon as they open, right? And N of 0 is going to be the number of people in line, right? So what does N of 3 mean? So n of 0 is the number of people in line after 0 hours. So what does n of 3 mean? Number of people in line after 3 hours. So if they equal, what does that mean? So at opening, which is our 0 hours, and 3 hours later, there is the same number of people in line. All right, then we have n of 4 is greater than n of 6. What does that mean? There are more people in line after 4 hours than 6. All right, then we have n of r equals 34. We don't know what r is. It's just there as a variable. So what does that mean? Or at r hours. What's happening at r hours? 34 people are in line. That would not be a line I was waiting in. Not with 34 people in front of me. It must be some really good food to wait for 34 people. Maybe they are, who knows. But, okay, so today we looked at evaluating functions at specific inputs, okay, putting them in function notation, and doing the input and output, our domain and range, in context. Okay, so we're going to keep looking at function notation over the next couple of days, and we're going to look at different things when we look at it. So, we are done for today.